welcome to all of you. Feel free to ask questions at any time, and you can do that either orally or through the chat. I'll be looking at the chat box rather than at your faces, so I hope I'll be able to get to all of your questions. I hope everyone can see my slides. Let me tell you what I intend to do in the 3 sessions before me. I want to begin by asking and answering the following question, which is, why do we need markets to allocate resources? Why do markets even need to be designed? And then I will go on to the technical issues that arise when you think seriously about designing a market. And there my focus will be on the problems that are particular to the allocation of indivisible goods. So why use markets to allocate scarce resources? The argument is an old one going back at least to Adam Smith, which took about 200 to 300 years to formalize, and which I can summarize as follows. Subject to certain assumptions that are explicitly laid out, markets deliver outcomes that are coherent, which is a fancy way of saying feasible, supply meets demand. In a precise sense, those outcomes are unimprovable, meaning Pareto optimal. And under certain conditions, you can argue that those allocations are fair. So this is the argument for why we want to use markets. But if you look at this list, you would have to say, wait, why can't I achieve these very same outcomes through central planning? Why do I need a market to do this? If my goal is Pareto optimality, simply solve the problem of finding a Pareto optimal allocation. Why fuss around with prices? Well, central planning has a history. It's a little shorter than the history of the reason for why markets are a good way to allocate resources. But central planning is deficient in a very particular way that I'll get to. But here I will summarize what I think is perhaps the most damning criticism of central planning by an economist, John Jukes. It has no theoretical foundation. Intellectually, it is a vacuum. And I'm saying this, even as Vohra pointed out, that we are technically in the birthplace of Karl Marx, and central planning is sometimes associated with Marxian thought. Okay. Now, why not rely on central planning? And it's an old criticism, which is it's the problem of information. And there are 2 kinds of problems of information that it's important to distinguish. The first I'm going to call a physical problem, which is just the sheer difficulty of recording, summarizing, retrieving, and transmitting the data that would be needed. And I have here a quote from Jo Langer, who some of you may recognize as the wife of Oskar Langer, who was I think he was Czech, but he was, when Czechoslovakia was under Soviet rule, he was a well-known dissident. But as you can see from her, this quote I've taken from her biography, she describes the problem, I think, very well. In December, the head of the planning department asked me to make out a table showing exactly how many toothbrushes, what sort of bristles, what colors, etc. I was planning to deliver to Switzerland, England, Malta, Madagascar, and so on during the first half of the coming year. I said that I couldn't possibly know, as our agents in various places were ordinary mortals and as such were subject to illness and death. My objections were waved aside, and I was told to draw up my forecast without delay. Okay, so this paragraph points out that there's just this basic difficulty with collecting the information. And recently, there is a school of thought that has argued that this problem no longer exists. Data science, artificial intelligence, machine learning, pick whatever your favorite new definition of statistics is. The argument claims is that this problem is no longer relevant. Central planning is back again. A colleague of mine refers to this as the hipster central planning movement. Right? But this ignores the second problem of information, which I think is the more important one, which is the strategic problem. Much of the information that we require to allocate resources in some desired way is dispersed and privately held. And I put down privately held in boldface to emphasize that that's the crucial constraint. If information affects outcomes, the holder of that information has an incentive to either corrupt it, conceal it, or misrepresent it. Okay? This is the fundamental difficulty that central planning faces. Okay? And those of you who have at least looked at what happened in the Soviet Union when they attempted central planning on a grand scale through their ministry, churning out plans, Gosplan, I think was the name of the ministry, will be aware that their fundamental difficulty was not so much collecting the information and collating it, but getting managers in the various factories to truthfully reveal the information about their inventories and their productive capabilities. And this is where markets dominate over central planning, in that they confront this problem of private information, and the intuition is that the use of market mechanisms causes this information to be elicited in a way that is relatively free of corruption. Okay. So that's the argument for why we would want to use markets to allocate scarce resources. The second question I said I would also spend some time answering is, well, why do markets even need to be designed? There are prices, trade takes place. Okay? Well, this is not true. Markets don't exist or even scale without institutions that support property rights and resolve disputes. Okay? Even companies that sell themselves as platforms like Uber and Airbnb, a major focus of what they do is precisely this: specifying the property right and resolving disputes. Okay? They cannot function without doing these two things. Okay? The second reason markets need to be designed is that a market will fail to deliver the promised desirable outcomes when externalities are not priced in. So let me remind you of what an externality is. An externality is said to occur when my consumption of some resource affects your utility. And I could affect your utility in either a positive or a negative way. Externalities are a feature of connected communities. They're unavoidable. Some externalities are so commonplace that we don't even recognize them as such. Bad breath, flatulence are examples of negative externalities. We do not stay up nights worrying about how to deal with those particular externalities, because in the grand scale of things, they're not that important. In those cases, we typically rely on customs to limit those particular externalities. And there are other externalities that are more significant, and perhaps the most prominent at the current is the decision of whether or not to take a vaccine. My decision to take a vaccine confers a positive externality on you, in the sense that if you come into contact with me, the chance of infection is lowered. And likewise, if I don't take a vaccine, then any contact with me increases the chance that you will become infected. Now, there is a substantial externality which is not priced in any way, and which we currently deal with through regulation in some parts of the world. Okay? So I want to make one more point here. You will sometimes hear sentences of the following kind. Markets fail when there are externalities. This is an incorrect interpretation of what the theory tells us. What the theory tells us is that when the externalities are priced in, the market works. Okay? And so the central technical challenge of market design is figuring out how to price in the relevant externalities. That problem I would describe as the public-facing aspect of market design. This is what appears in the published papers and books. But there is also a tacit aspect of market design, which does not appear in papers or books, but it is part of the general informal conversation among the community, and that is the design of the property rights themselves. Okay. And I think this is a particularly important point that I want to spend a little bit of time on it with an anecdote. As many of you know, spectrum auctions are frequently held out as one of the shining successes of market design. Okay. Prior to the use of auctions, spectrum rights were allocated by what was known as a beauty contest, which means that a company wanting spectrum would go to the relevant civil servant and basically say, look at me, look at how nice I am, give me a spectrum license. At least in the United States, under a Reagan administration, the decision was made to switch from beauty contests to running an auction, auctioning off spectrum rights. But now this raises the following basic problem. What exactly is a spectrum right? Okay. Well, the basic externality that they were concerned with, which is why were you giving out licenses to spectrum in the first place, is interference. If I hand you a license and I hand someone else a license, that license should allow you to communicate wirelessly without interfering with each other. Okay? So it seems obvious that when we design a spectrum license, we should design it in such a way that we guarantee little or no interference from holders of other licenses. Okay? Now, traditionally, this has been done by specifying what are known as guardrails. So if you think of spectrum as being a slice of land on a beach, I give you the slice of land on a beach plus a little bit of land on either side so that I limit the interference from your neighbors. Now, this seems relatively benign, but it ignores the fact that the amount of interference you suffer is a function of your technology choice. Interference is a function of how smart my antenna are. It's a function of how good my decoding algorithms are. If I specify licenses with wide guard bands, it reduces the incentives to build and design sensitive antenna and improve decoding algorithms to separate noise from information. So my point here is that specifying the property right is not benign. It has knock-on effects in terms of the actions and investments that the agents will have to make, in this case, in technology. Okay. Let me pause here for questions if there are any. Okay. So since the remainder of the discussion will be technical, I will not be discussing in great detail this issue of property rights, how you design them, but I want you to keep it in mind. Okay? When designing a market, this is an important thing to concern yourself with. I want to now focus on the technical issue of how to price the relevant externalities. And there is one particular externality that we are all so familiar with that we don't even think of it as an externality, which is the one associated with me consuming a good. If I consume a Van Gogh, meaning I own it, it prevents you from owning that Van Gogh. That is a negative externality. We never think of that as an externality because that's the sort of externality that the market naturally prices in. Okay? So I want to begin with the simplest possible market setting you could imagine. And the reason I want to do this is because this example, I think, should represent what we are aiming for when we are designing a market. Okay? And because it's simple enough, I think I will be able to convey the main technical issues without being befuddled either by notation or complicated mathematics. And so what is it? I have a seller with a single indivisible good. Their opportunity cost for the good is 0. There are a set capital N of potential buyers. Each buyer has a monetary value for the good, and I'm going to denote buyerized monetary value by VI. And there are no liquidity constraints. Okay? Now, in those 4 sentences, a couple of important assumptions are embedded, which I want to make explicit. First, there is an available medium of exchange, money. Second, the supply of money is not a limit on any activity. Third, preferences are restricted. Everyone's preferences can be denominated on a common monetary scale. These are restrictive assumptions. As I said, the model is very simple, and it's important that you keep those assumptions in mind. Okay. Now, if I were designing a market for how to allocate this good, the first question I should ask myself is, what is it that I wish to achieve with this market? In other words, what is my goal as the planner? And notice I am using the old-fashioned word planner, which probably connotes images of aged civil servants in dusty basement offices in a small town like Bonn. I could have chosen the sexier word designer, which I think connotes Silicon Valley entrepreneur, but I'm old-fashioned. I will go with planner. Okay. And I'm going to make the assumption that the planner's goal is to allocate the good so as to maximize efficiency. And efficiency in this context is well defined precisely because everyone's preferences are denominated on the same monetary scale. I wish the good to go to the person who values it the most. Okay. Now, you could say, why that objective? Why not some other? And the short answer is, if you prefer another objective, go to another session. This is the objective that I want to look at. Okay? But what I want you to focus on is not so much my choice of objective, but the approach that I'm going to take. Okay? So I have an objective specified. The next thing is, what is the optimization problem that the planner would have to solve to achieve this objective? Well, that's the problem that I can formulate as an integer program. And so I'm going to introduce a decision variable x subscript j, take the value 1 if the good is allocated to buyer j and 0 otherwise. And here, I'm going to introduce a little bit of generality that I'm not going to use just yet, but I'd like it later on. For any subset S of agents, I am going to look at the problem of efficiently allocating the good to the agents in the set S. So I'm defining not a single optimization problem, but I'm defining one for every possible subset of agents. And so what is it? Maximize sigma vj xj. So maximize the sum of the values, subject to the constraint that no more than one agent receives the good. Notice I have inequality, which means I'm allowing myself not to give the good to one of the agents in N. In other words, the good can be retained by the owner of it. the little xj's have to be either 0 or 1. Now, this is an utterly trivial integer program. And as you can see, capital V of S, which represents the value of the efficient allocation, is simply the largest VI in the set S. Any questions so far? Okay. Now, the reason why I stated an optimization problem, not just for all of the agents in N, but for any subset of agents in S, is because one of the things one should be concerned about with designing a market is how do you know that anyone will turn up? And therefore, I need to be able to think about what happens if only a subset of the agents choose to participate. And this is the reason why I've introduced this slightly more general notation right now. Okay. Now, that integer program that I put up, I am now going to write down its linear programming relaxation. That's what you see at the top of the slide. And I'm looking at the problem involving all of the agents in N. Now, my original problem as the planner is to solve an integer program. I am now writing down a linear program. But again, this is such an utterly trivial linear program that we know that this linear program has the integrality property, meaning all of its extreme points are integer value. So here is a sketch of the hyperplane that describes the feasible region. Here are the possible extreme points. And as you can see, each of the extreme points, at least in the two-dimensional case, are integral. That means my original planner's problem, which was written as an integer program, is in fact a linear program. So I'm going to solve the linear program. Now, the beauty of linear programming, of course, is that we have access to a strong duality theorem. So the next thing I'm going to do is assign dual variables to each of the constraints. So to this constraint, the resource constraint, I'm going to assign the dual variable little p, which I'm going to subsequently interpret as a price. Now, these constraints here, xj less than or equal to 1, these are redundant constraints. If I were just concerned with solving the optimization problem, I would typically remove them as being unnecessary. But these redundant constraints have economic meaning. And the reason they have economic meaning is because I'm going to interpret the dual variables as prices. Keeping in these redundant constraints means that I may have multiple optimal dual solutions. This is not a bug, this is a feature. And you will see why this is a feature in a moment. So the dual variable associated with this constraint, I am going to call Sj, and I'm going to interpret, as you will see, Sj as the surplus that buyer J enjoys. At the bottom of the slide, I have written down the dual to the linear program that appears in the top half. Let me pause so that you can check that I have indeed written down the dual correctly. Okay. Now let me convince you that it is reasonable to interpret the Sj variables as surplus. If I look at this constraint, if you gave me the value of P, then it is obvious that I should set Sj equal to the following. The maximum agree? Notice that term maximum of Vj minus P comma 0, that is the surplus that agent J would enjoy if they bought the good at price P. Now, how does that help me? Well, let's actually solve the dual. And to avoid annoying tie-breaking issues, I'm going to assume that the valuations of the agents are ordered from largest to smallest with no ties. So agent 1 has the largest value, and agent 2 has the second largest value, and so on. And what is the optimal solution here? Well, there are multiple optimal solutions, and the optimal solution appears at the bottom of the slide. Any value of P between V2 and V1, S1 equal to V1 minus P, and all the other SJs equal to 0. Now, how do I know that this is optimal? Well, I know what the optimal primal solution is. The optimal primal solution is give the good to agent 1. All other variables are 0. So in order to verify that what I've given you is an optimal dual solution, it suffices for you to check complementary slackness. Okay. Now notice in the primal, the resource constraint is binding. The price variable is positive because I'm assuming valuations are bigger than 0, otherwise this is not interesting. And so therefore, complementary slackness holds there. And what's the other complementary slackness condition that I need? It is this. And you can verify for the choice that I've given you that that indeed holds. Now, why is this interesting? Well, if I interpret the little p as a price, this tells me that there is a price that I can choose where supply exactly meets demand, where demand is defined as a buyer will agree to buy the object if it maximizes their surplus. And in this case, the buyer has a very simple choice, either buy or not. So a buyer will buy as long as their surplus is non-negative. Furthermore, at this price, not only does supply meet demand, the person who gets the object is the person who values it the most. So I'm also getting the efficient outcome. Let me summarize this. There is a range of prices at which supply is equal to demand. Remember, the range of prices is between the second highest valuation and the highest. At any of these prices, the person with the highest value gets the object. So that's the efficient outcome. And here is the last important observation. There is in this interval, let me remind you what the interval is. There is one price that is best for the seller, V1, and there is another price that is best for the buyer, V2. There is no price that is simultaneously best for both. This is an illustration of a more general principle. Whenever you have a market consisting of two sides, where one side wants what the other side is offering, you will not be able to find an outcome. You are not guaranteed to find an outcome that is simultaneously best for both sides. Okay? Now, this is important for the designer because it means that the choice of price has welfare effects. Which price your market mechanism determines affects the distribution of surplus. And that in turn could affect decisions by agents about whether to participate or not in the market that you're proposing. Now, so far in what I've described, you can legitimately say all of this is utterly pointless. At the end of the day, you had a well-defined optimization problem. Then you went through this rigmarole of defining prices. When your goal was to simply give the object to the person with the highest value, why not just do that? Okay? And it's the informational problem. So here is the challenge now for the designer. I know there are prices that will produce the efficient allocation. How do I find those prices if I don't know what the VIs are? Does this question make sense? Now you can say, why not just ask everyone? Well, if I know that the price that you set is going to be influenced by what I tell you is my value, that's going to give me an incentive to shade my value down. That's the informational problem. There is a second problem, which is what are the incentives for any agent to participate in this market that I'm going to design? Okay. I've intentionally called this a stability problem rather than a participation problem, because in the economics literature, participation typically means that the agent has some outside option that is exogenously given, and they will participate as long as you offer them more surplus than this exogenously given outside option. In my view, that's very limited. The outside options for agents are typically not exogenous. They are endogenous in the sense that when I choose to break away from the market, I could break away with other people who are participating. And therefore, my benefit of breaking away from the market may depend on who else breaks away from the market at the same time. And hence, I'm using the term stability rather than participation. Everyone with me so far? Now, for this toy problem, let me focus on the informational problem. I will give you two methods for solving the informational problem. The first is the now famous seal bid second price auction, credited to William Vickery. Each buyer submits a bid for the object. Highest bidder wins. Winner pays the second highest bid. So let me remind you of notation. Here are the actual valuations of the agents. And remember, I ordered them in decreasing order. Every agent submits a bid. Who knows whether they submit truthfully? Highest bidder wins, but pays the second highest bid. It's a well-known result that when you formulate this auction as a game, it is a dominant strategy for each bidder to bid their value. That means bidder 1 will bid V1, bidder 2 will bid V2, bidder 1 will win the auction and pay V2. In other words, the winning bidder will pay one of the possible market clearing prices, and in fact will pay the smallest of the market clearing prices. Recall, any price in this interval was such that supply was equal to demand. In other words, this particular mechanism produces an outcome that favors the buyer. And the reason it does that is to give the buyer an incentive to reveal their private information. So if you have hopes of building a mechanism that will favor the seller, in other words, generate that price, V1, the most favorable price to the seller, you will not be able to achieve that if simultaneously you want to give the bidders, the agents, an incentive to truthfully reveal their valuations. So this illustrates another general principle, which is in order to get people to tell the truth, you have to bribe them. And this is the way in which economists are different from lawyers. Lawyers believe that you have to bribe people to lie. Economists believe that you have to pay people to tell the truth. Is this the only way you could get the agents to truthfully reveal their valuations? The answer is no. Here is another auction that one might run. This is called the ascending clock auction. There is a price clock at the front of the room. In front of every bidder is a button. Bidders start by pressing the button. The price is set at 0. As long as 2 bidders are pressing their respective buttons, the price on the price clock rises continuously. The moment 1 bidder is left, the auction stops, and that bidder is the winner, and they pay the price shown on the clock. Everyone understand the rules? Again, it is not hard to show that when you formulate it as a game, it is the dominant strategy for every bidder to remain active until the price clock hits their value, which means that the winning bidder will be the person with the highest value, and they will end up paying the second highest value. So the outcome in that sense is the same as the seal bid second price. Is there a reason to prefer one over the other? The answer is absolutely, for reasons that are not part of the model that I described. Okay. The 2 different mechanisms impose different burdens upon the bidders. In the first one, the bidder must think about their value ahead of time, which could conceivably be a complicated problem for them. In the second, the bidder simply has to ask a weaker question, which is, does my value exceed the current price? Even though there is a dominant strategy equilibrium to both of the corresponding games that delivers the same outcome, it doesn't mean that these 2 market mechanisms are the same. One corresponds to a static game, the other corresponds to a dynamic game. And as we know from game theory, even though any dynamic game can be written as a static game and vice versa, that transformation is not benign because it introduces other equilibria. When we move from the static to the dynamic version, the old equilibria in the static version are preserved, but the dynamic version may introduce equilibria that were absent in the static version. And then you have an issue of, should we be concerned that the bidders may play these other equilibria? And in this context, there is an equilibrium that is observationally equivalent to the bidders colluding to depress the price. And so a concern one would have as a designer is when you move to this kind of clock auction or dynamic mechanism, you are allowing for more equilibria. How plausible are those equilibria? Are the buyers likely to identify them and play them? And what is the effect on the distribution of surplus? Any questions so far? Now, the stability consideration. How do we model that? So to do that, I want to make a digression to the subject of what are known as transferable utility cooperative games. This was a central subject of the von Neumann-Morgenstern book on game theory. For the first 15 years in the history of game theory was an extremely popular subject, but since then it has fallen out of fashion, no longer taught, I think, in most PhD programs, which I think is unfortunate because it's a useful way to think about the stability issue. Oddly enough, it does crop up when people talk about matching, but they never refer to cooperative games. That's because cooperative games are simply unfashionable, and if you refer to them, it's clear that you're old-fashioned and out of touch. Okay? And since I am both of those things, I'm not embarrassed about referring to cooperative games. So let me first describe what a transferable utility cooperative game is, and then connect it back to the question of designing a market. We have a set N of players, and associated with any subset of players, which we typically call the coalition, is a value V of S. And here is the interpretation that you should have in mind. Every one of the players is in possession of some productive resource. If the players in S were to get together and combine their productive resources, they would be able to generate a monetary value of capital V of S. Now, loaded into that interpretation is the assumption that when you and I get together in some coalition to combine our productive assets or resources, we do so without strategic concerns of any kind. So for example, if to generate value from those productive resources, we have to put in costly effort, then the assumption is that we will each work to the best of our ability. We will not shirk. If putting those productive assets to use in the most efficient way requires us to share private information that could have a negative effect on oneself, the assumption is it's not a concern. We share the information freely. Okay? So in other words, when a group of agents get together, all strategic considerations are ignored. V of S represents the maximum achievable value that the agents can obtain, absent any strategic considerations whatsoever. Okay? And there are some technical assumptions that we impose on V. One is sub-additive, and the reason for that is obvious, which is we are interested in when agents have an incentive to get together, and sub-additivity would be a minimal requirement for that. Sorry, do I want sub-additivity? No, I want super-additivity, sorry. I would want something like this. Okay. Now, what's an allocation in this game? It is a division of the total surplus, and the total surplus is the value that could be generated if everyone in N pools their resources together. Okay. Now, a technical term. You propose an allocation, which is a point in this simplex that I just boxed. That allocation is blocked by a coalition of players S if the following is true. In other words, you, the planner, told all of the agents, get together and pool your resources. You will generate V of N. Then you, the planner, proposed a division of V of N. Those are the ZIs. A group of agents looked at what you proposed and said, wait a second, if we break away, we could generate more value ourselves than what the planner is proposing. If that is the case, why should we listen to the planner? This group S has an incentive to break away and do things on their own. That is why we say that your allocation Z as the planner has been blocked by the coalition S. What is the core of a cooperative game? It is the set of allocations that are unblocked. In other words, the set of allocations described by the following collection of inequalities. Notice there is one inequality for every subset of players. So the core is, the description of the core is exponential in the number of agents. This is not something that need concern us because typically the V of S will have structure. So the fact that the core has this complicated description will not be an issue. What should concern you is that the core is not guaranteed to be non-empty. And it's not hard to come up with examples of where the core is empty. But when it is non-empty, this is a wonderful thing. Why? Because if you, the planner, pick an allocation that lies in the core, then no coalition of agents has an incentive to break away and set up their own exchange or competing market. And importantly, they have no incentive under a very strong sense of incentive, meaning when the agents break away, we assume that the agents do not have to solve any incentive problem themselves. So when a coalition breaks away, we're assuming that they can achieve the maximum possible value that is achievable without having to be concerned with any incentive problems within their ranks. So the core is an extremely strong condition. If something is in the core, I do not have to model what happens when a group of agents break away. When they break away, what are they doing? What's the game they're playing? None of that is relevant. Because in whatever game they're playing, they cannot achieve more than V of S. And in the core, I am guaranteeing them a surplus of at least V of S. It's a very strong notion of stability. Okay, now let's return. There is, by the way, a necessary and sufficient condition for the core to be non-empty, which is credited to Bondareva and Shapley. I won't go into it just yet because I don't need it, but it's a direct consequence of the duality theorem of linear programming. What I'm going to do now in my market consisting of a single good is I'm going to associate a transferable utility cooperative game to that market and then argue that the market outcome is in the core. And because it's in the core, that tells me that the market design that I'm proposing has the feature that no group of agents has an incentive to break away. In other words, when I propose my market design, the agents are going to turn up. So here is the way I'm going to set up the cooperative game. I have a set N, these are the buyers, and I'm going to use sigma as before to denote the seller. So the players consist of the buyers and the sellers. The value of a coalition consisting of the seller and a set S of buyers is this, sorry for the typo, is this V of S that I defined as follows. The value of the efficient allocation restricted to the seller and the buyers in the set S. Okay. Any coalition of buyers that does not contain the seller, I assign that coalition 0. This is a transferable utility cooperative game. The core is non-empty. Let me convince you of that. Let me write down what the core is for the case of just 2 agents. Agent 1 has a higher value than agent 2. Z1 is the surplus that I promise agent 1. Z2 is the surplus that I promise agent 2. Z sigma is the surplus I promise the seller. If I put all 3 of them together, the maximum total value they can achieve is V1. Any coalition consisting of agent 1 and the seller can achieve value V1. Any coalition consisting of agent 2 and the seller can achieve value V2. Any singleton coalition achieves 0. Here is one of the market outcomes which corresponded to the second price auction. The seller receives V2. Agent 2 receives nothing. And agent 1 walks away with a surplus of V1 minus V2. I'll pause for a moment so that you can verify that that is indeed in the core. Is it the only point in the core? The answer is no. Here's another one. All of the value goes to the seller. That is also in the core. So the outcome that benefits the buyer and the outcome that benefits the seller the most are both in the core. Any questions so far? So now I can come to the climax of this little model. For allocating a single indivisible good, I have the following market design. Run a second price auction. The agents will have an incentive to truthfully reveal their valuations. This will produce the efficient allocation. This produces an allocation that is in the core. That means no subset of buyers has an incentive to approach the seller privately, say, and make the following offer. Why don't we forget this market that's being proposed by the planner and we trade among ourselves? That cannot possibly improve the surplus that they would enjoy. So the market design that I'm proposing is stable in the sense that the agents have an incentive to participate and no subset of agents has an incentive to break away. Okay. Any questions? Now, let me make a comment about the relationship between the core and the set of optimal dual solutions to the problem of finding the efficient allocation. At the top of the slide, I have written down the dual to the problem of finding the efficient allocation. Okay. Every optimal solution to the dual lies in the core. And the following is also true. Every point in the core corresponds to an optimal dual solution. I'm not expecting you to see this right away. It's worth thinking a little bit about. But the reason I'm pointing this out is that the core is described by an exponential number of inequalities. But if you buy what I just said, in this particular example, the core can be described by a system that is much smaller than exponential. Okay. In terms of proving it, at the bottom, I've written down the core conditions. Okay. If you think a little bit about what complementary slackness means in this case, that's enough to give you the argument of equivalence. Okay. So this is a very strong relationship. Every optimal solution to the dual corresponds to a competitive equilibrium outcome, meaning a price at which the market clears and we get the efficient allocation. Every competitive equilibrium outcome is in the core. This is true in general. The reverse, every outcome in the core is a competitive equilibrium, is not always true. It is true in this economy. So this is sometimes called core equivalence. And as a designer, why might you care about this? Because if there are multiple points in the core, it raises the issue of how you're going to divide the gains of trade up between the various participants. And as a designer, you might want some flexibility in that regard. Okay. I spent a lot of time on this simple example involving a single object. And the reason I did so is because I think this example describes the roadmap that one should be thinking about when designing markets for allocating indivisible goods. And here I've summarized the roadmap. Formulate achieving the planner's goal as an optimization problem. If duality holds, dual variables can be interpreted as prices. Complementary slackness means the dual and the primal can be interpreted as competitive equilibrium outcomes. Competitive equilibrium outcomes are in the core, so a strong notion of stability is satisfied. And the last problem you now face is designing a mechanism to elicit sufficient information to identify competitive equilibrium prices. Okay. So this, if you like, is my 5-point plan for designing markets. What are the catch? What's the catch? The catch is I told you this story in the context of quasi-linear preferences, unlimited availability of a medium of exchange, and strong duality. And you can say to me, look, those things cannot possibly hold in all circumstances. So how on earth could this roadmap be useful except in the most trivial of cases? And my short answer to that is you would be wrong. Okay? This roadmap is useful even when we relax each and every one of these conditions. Okay? And this is what I'm going to try and convince you of in both the remainder of this and the subsequent sessions. Okay? Any questions before I continue? Okay. Let me tell you now what happens when duality fails.
Sir, what is the reason for the duality?
Say again?
Why did you use duality, sir? In primal we get the solution, in duality also we get the same solution.
Remember, I spent some time interpreting the dual solution as prices. And the reason I did that is because I need the interpretation of prices to argue that there is going to be a market that obtains the primal solution. Does that make sense?
Okay, sir.
Okay. And I'm going to emphasize this point again with the following, in the following. I am going to move now from allocating a single object to allocating multiple objects where agents are potentially interested in consuming subsets of objects. I am going to touch on a couple of points. This particular environment, Martin, in his lecture, will go into in greater detail than I will here. Okay? But it will give me the opportunity to alert you to some of the issues that Martin is interested in dealing with. Okay? Okay. Even when duality fails, I want to argue that my roadmap is still useful. And I want to convince you of that with the following setup. As before, I have a set N of buyers. I have a set capital M of indivisible goods. For every subset S of goods, and for every buyer I, they assign a monetary valuation to the bundle of goods S, which I'm going to denote by VI of S. VI of the empty set is 0, and I'm going to assume that VI of S is monotone, meaning you assign more value to a superset than to a subset. A bidder who consumes a subset S and must make a payment little p for that privilege receives a net payoff of VI of S minus p. That's the quasi-linearity assumption. Okay? So I'm keeping quasi-linearity. I'm keeping the availability of a medium of exchange that is available in unlimited amounts. What I am changing is the fact that I'm no longer allocating a single good. I'm going to follow my roadmap. I'm going to write down the optimization problem that the planner solves. So X subscript J of S is 1 if I give the subset S of goods to agent J and 0 otherwise. Sorry, I made a typo. That should be I. And now I've written down an integer program to find the efficient allocation. So let me go through it. This is whether I give the bundle S of goods to agent J or not. This is the value that agent J enjoys. What am I summing over? Over all agents and over all possible bundles of goods. Okay. What are my constraints? Well, let's start with this one that I'm boxing. For every agent J, I am giving them no more than one bundle. What is this one? For every good I am handing out no more than one bundle that contains that good. So I'm assuming that each good is available in only unit supply. So I'm looking at all bundles that contain the object I, and then all of the agents who might receive such a bundle, that adds up to less than or equal to 1. That's an integer program for solving the planner's problem. Now I'm going to take the dual. To each constraint of this form, which corresponds to the good, I'm going to assign the dual variable pi, which I'm going to interpret as the price of good I. And to each constraint that corresponds to an agent, I'm going to assign a variable Sj, which I'm going to interpret as the surplus of agent J. Okay. And now what will the dual look like? Here it is at the bottom of the slide. I am minimizing the sum of the prices plus the sum of the surpluses. I am minimizing producer surplus plus consumer surplus, subject to the following constraint. And this constraint you've seen before in the case of a single good. It was simply Sj plus the price of the good must be bigger than or equal to the value that that agent enjoys. If you hand me the prices, each Sj is what? It's the following. Over all bundles of goods S, I choose the bundle that maximizes my surplus unless it's negative, in which case my surplus is 0. Any questions? Now, if duality holds, what does this tell me? It tells me that I can support a competitive equilibrium allocation using prices on individual goods. If duality fails, this tells me that I cannot support a competitive equilibrium allocation using prices for each individual good. Now, how is that useful practically? Okay, I have a bunch of objects that I wish to sell. You come to me and you say, I have a fantastic idea. Auction off each object separately. That will produce the efficient outcome. At this stage, I do not need to construct a complicated game and work out the equilibrium. I just say to myself the following. If what you say is true, that you can produce an efficient allocation by auctioning off each good separately, your auction is using prices on individual items only, which means that you are telling me that you can find individual prices that support the efficient allocation. In other words, you are telling me that strong duality holds. But if strong duality fails, then I look at you and say, you're talking through your hat. There is no way that you can guarantee that you achieve the efficient allocation. Why? Because the failure of duality means that I cannot support an efficient allocation using prices on individual items. Does this point make sense? Now, failure of duality only means that the formulation that you wrote down doesn't satisfy duality. Okay? However, I cannot say this enough. Everything can be written as a linear program. I'll say that again. Everything can be written as a linear program. What's the catch? You have to allow me as many variables as I like. So the fact that this integer program does not satisfy strong duality does not mean that there isn't some other integer program that will do that. And we know how to do that. It's what's called the extended formulation. We simply throw in additional variables. Now, why is this useful? Let me show you why. In fact, it's easy to convince yourself that duality fails in this example. Just think of bipartite matching on a triangle, which you can interpret each node of the triangle as a good. Each edge corresponds to an agent who is interested in consuming only that pair of goods. Let me describe an extended formulation for the problem of efficiently allocating the goods. Okay. The way this extended formulation works is you essentially introduce a variable for every possible solution. This is why strong duality holds. Now, you may say, from a mathematical programming point of view, this seems like an utterly ridiculous exercise. The goal is not to set up a formulation that's so large that it's impractical. Okay? But you would be missing the point. The reason for setting up this impractical linear program is to understand what kinds of prices are needed to support an efficient allocation. Okay? So here is the extended formulation. I'm going to use the symbol mu to denote both a partition of the set of objects and an assignment of the elements of the partition to the bidders. So here are my objects. Sorry, I went too far. Here are my objects. What's an instance of mu? It's a partition of the objects. So here is a partition. There are 3 elements in the partition. This one goes to agent number 1. This one goes to agent number 2. This one goes to agent number 3. That is an instance of mu. So mu is a list of all of these partition assignment pairs. Large number of mu's, don't care. Gamma is the set of all partition assignment pairs. Mu subscript j means that under mu, bidder j receives the bundle mu j. Delta mu is 1 if you, the planner, select the partition assignment pair mu, and 0 otherwise. Now here is the formulation. Maximize total value. Okay. Let's start at the bottom. You must pick one partition assignment pair. No agent receives more than one bundle. I can only give agent J bundle S if I select a partition assignment pair in which agent J receives bundle S. Let me pause here to allow the formulation to sink in. Now what I'm going to do is assign now this integer program has the integrality property. Okay? And that you can see from the fact that I basically encoded every possible feasible integer solution as a variable. Because it has the integrality property, duality is going to hold. And now let me assign dual variables to each of the constraints and interpret them. So to this constraint, I'm going to assign the dual variable pi, which I'm going to interpret as the surplus or the profit to the seller. To this one, I'm going to assign Sj. This is the surplus to the buyer. And to this one, I am going to assign P subscript Js. Because notice there is one constraint here for each J and each subset. What is Pj of S, the interpretation? It is the price that Mr. J pays for the subset S. Now, what this means is I can support an efficient allocation using prices, but the prices have to be discriminatory, meaning Pj of S need not be the same as Pj prime of S. In other words, two different agents may end up paying different prices for the same bundle. And second, the prices will be non-linear. Meaning the price of a bundle is not necessarily the sum of the individual prices. Now, earlier I said one of the challenges in market design is figuring out how to price externalities. What this simple analysis tells me is that if I want to guarantee the efficient allocation, I have to be willing to live in a world where prices are both non-linear and discriminatory. And now we come to a practical problem, which is, can we find such prices? How difficult is it to do that? Okay. And then there are trade-offs, which is if you make the prices discriminatory and non-linear, the decision problem for the agents, which bundle should they buy at a particular price, becomes complicated. And these are the kinds of things that Martin worries about. In other words, you're trying to find some sweet spot. You would like your price functions to be rich enough to account for various externalities, but not so complicated that computation becomes difficult for the participants in the market. Does this make sense? So notice, even though duality did not hold with my initial formulation, the roadmap that I described was still useful because it pushes me in the direction of thinking about what is it about the kinds of prices that I need in order to sustain an efficient allocation as a competitive equilibrium. Here's the dual formulation. Now, just to complete the circle, what about stability? Well, I can do the same thing. I can associate a transferable utility cooperative gain in the same way as I did before. I'm now using pi to denote the surplus or the profit to the seller. This is the surplus to the buyers. These represent the value of the efficient allocation involving the subset S of the agents. Okay. You can still prove that the set of optimal solutions to the dual coincides with the set of points in the core. So you get core equivalence. Okay. What about incentives? Well, we are now moving to a more general setup where agents are consuming bundles of goods. The second price mechanism, doesn't have any bite here. There is a generalization of it called the Vickery-Clark-Groves mechanism. So there is an auction mechanism for allocating the goods to the agents in such a way that it is a dominant strategy for the agents to bid truthfully, and you are guaranteed to get the efficient allocation. I'm not going to go into the details of this. What I want to emphasize is that the key feature of the Vickery-Clark-Groves mechanism is that it gives to every agent a surplus that is equal to their marginal product. Recall what I said before. In order to get agents to tell the truth, you have to pay them. The Vickery-Clark-Groves mechanism pays every agent their marginal product. What is the marginal product? Value of the efficient allocation that includes everyone, minus the value of the efficient allocation that excludes you. That difference represents the value that you as an individual bring to the economy. So what the Vickery-Clark-Groves mechanism is basically saying is participate, and then you say, well, look, if I walk away, you're going to lose Vn minus V of n minus I. Pay me that, and I turn up. Okay. Why am I commenting on this? Look at the conditions for the core. Pick one of these constraints. That includes everyone but agent J. Subtract this and add to this, and what do you get? Sj is less than or equal to Vn minus V of n minus J. And that's the marginal product of J. In other words, in the core, no buyer can obtain a surplus that exceeds their marginal product. If I want to be in the core and give all buyers the incentive to truthfully reveal their valuations, I have to find a point in the core that gives every buyer their marginal product. Is that guaranteed? The answer is no. You can find examples where that is not true. So you can ask for a sufficient condition, which is basically plug in the fact that you want every buyer's surplus to be equal to their marginal product, grind away on the algebra. This is the condition that you need. It's a form of it's a weaker condition than submodularity. Okay? It is a condition not on the individual preferences of the agents, but on the capital V of n, the value of the efficient allocation. Here is the interpretation. What is this object on the left? This is the marginal product of the coalition n minus s. In other words, if the group of buyers in n minus s gets together and walks away, the left-hand side is the drop in value that you would see. What is the right-hand side? It is the sum of the individual marginal products of the agents in n minus s. Translation, if the agents act together, which is the left-hand side, their marginal product is higher than if they act independently, the right-hand side. In other words, the buyers will have more power if they act as a group than if they act individually. If that condition is satisfied, then there is a point in the core that gives every buyer a surplus equal to their marginal product. So therefore, amongst the set of nonlinear discriminatory prices, I can find one that supports an efficient allocation and also gives the agents an incentive to truthfully reveal their information about their preferences. But it requires this joint condition. Now, is this condition true? It is true in certain circumstances, but not always. And when it fails is when you're going to have problems as a designer with stability and incentives. Because if you want to give the agents an incentive to truthfully reveal their information, you have to give them their marginal product. But if the marginal product is outside of the core, that could give some subset of agents an incentive to break away. If, on the other hand, if you want to ensure participation, that means you need to pick a point in the core, but then you may not have access to the relevant private information, which means you may be unable to pick something in the core, pick up something in the core. Okay, so there is this tension now between getting the incentives right and getting stability. And let me end here, as I think I've reached the end of my appointed hour and a half, and I'm happy to answer questions. Okay, let me remind you of where at least I am in the story that I want to tell. I laid out this roadmap in the first session, which is formulate achieving the planner's goal as an optimization problem. If duality holds, the dual variables can be interpreted as prices. Complementary slackness means that these prices and the primal solution together constitute a competitive equilibrium outcome. Competitive equilibrium outcomes are in the core, that you want that property because it says something about the stability of the market that you design. And then you have the challenge of designing a mechanism to elicit enough information to identify those competitive equilibrium prices. Okay. I also listed the following catches, which is that, the story I told you was in terms of quasi-linear preferences, unlimited availability of a medium of exchange, and strong duality. And towards the end of the first session, I dropped strong duality and discussed what might happen. Okay. What I want to do in this session is talk about what happens when you drop quasi-linear preferences and you drop the assumption of unlimited amounts of money, or in fact, even an available medium of exchange. Okay. Actually, so before I do that, I just remembered actually in talking about these duals, an amusing anecdote about Kantorovich. So as many of you know, the Soviet Union ran on a 5-year plan operated by a ministry called Gosplan. And the way that Gosplan initially worked is it would ask for factories to report to them their inventories and their productive capabilities, and then hand back a list of what the factory would have to produce in the coming period. Kantorovich and some of his assistants, because of their work with linear programming, then proposed an alternative. They said, let's collect the information as you're currently doing, and then we will solve a linear program to find the minimum cost way to produce the desired amounts of toothbrush and shoes that the state wanted. And the shadow prices on the supply constraints will be sent back to the managers of the individual factories. So that will be the information they will be given, and they will be scored based on those prices. Now, for those of you who are listening to the first half of this session, this seems like a perfectly sensible idea, except for the fact that you have to collect all this information and assume that the information is truthfully revealed. But what is interesting is that when Kantorovich was presenting this in a seminar, the question was asked of him by one of the party apparatchiks was, how did these shadow prices relate to the labor theory of value? Now, at this point, Kantorovich was on very shaky political ground. For those of you who subscribe to the Marxian orthodoxy, value should be related to the inputs of labor. Well, Kantorovich insisted that shadow prices were in fact the correct way to think about the value of labor. In fact, he said the shadow prices correspond to labor value. And this is a sign of how clever some of the Soviet apparatchiks were, because clearly this individual understood what was going on and said, but wait, you just told us that if a constraint does not bind, the shadow price is zero. That means even though labor has been put in, there is no value being assigned to the labor. And then for the next 10 years of his life, Kantorovich spent it trying to dig a hole, dig himself out of this hole to argue that shadow prices were indeed the manifestation of the labor theory of value. Anyway, history. Sorry for the digression. Okay, back to what I wanted to tell you about, which is I want to now talk about what happens if we drop the assumption of quasi-linear preferences and the unlimited availability of a medium of exchange, i.e. money. Can we still design markets to do desirable things? So as a warm-up, I first want to talk about a model that does have quasi-linear preferences and does have unlimited availability of money. In some sense, this is a benchmark, and it is the Shapley-Shubik assignment model. And those of you not in the economics tradition will immediately recognize this as bipartite matching. Okay? And here is the story. There is a set of buyers, B. There is a set of sellers, each selling one unit of a good. I'm going to assume the good is indivisible, and that good is commonly called a house. Vij is the monetary value that buyer I assigns to house J. And here is the crucial assumption: unit demand, no buyer is interested in more than one house. And for simplicity, I'm going to assume the same number of buyers as there are homes. Okay. Now, even though I've introduced a seller, in these models, the seller typically plays no strategic role whatsoever. So I can either have an individual seller of each house, or I can have a single seller who owns all the homes. Okay. Now, the reason why the seller plays no strategic role harkens back to a point I made before. To align the incentives, you have to pay people to tell the truth. And if you recall the example of a single object auction, in order to get the bidders to truthfully report their value, you have to pick the lower of the market clearing prices. In other words, you have to pick the market clearing price that is best for the buyers. Now, if the sellers had costs for the houses that they were selling, so that the costs would be their private information, since this model is entirely symmetric, you would have to pick the highest price among the market clearing prices in order to give an incentive to the sellers to truthfully reveal their cost information, which means you cannot simultaneously do both. Something has to give. So rather than focus on how you make that trade-off, we just assume that the sellers are non-strategic. Only the buyers are strategic. Okay. The reason why this model occupies a prominent place in economic theory is because there are a number of basic applications that can be folded into it. The most obvious one is the model of bilateral trade, where the houses are basically all the same, and so all the buyer cares about is getting a house, and the houses differ in their costs. There is another model, which is a model of labor markets, where the buyers are workers and the houses are firms. When a worker and a firm get together, they generate some output, which depends upon the characteristics of the worker and the firm. And so that the Vij could be the product of a worker type and a firm type. And therefore, the higher the quality of the worker, the higher the type of the worker, and the higher the type of the firm, the more output is produced. And the third application, which is perhaps the sexiest, is Google's keyword auction. And those of you who are going to stay around for the problem session after this talk, you will be asked to think through the Shapley-Shubik assignment model for that application. we'll do the usual thing. What's my objective as the planner? My objective as the planner is to find the efficient allocation. What is an allocation here? I'm assigning homes to buyers. So Xij, if buyer is allocated the home owned by seller J, and zero otherwise. And the basic constraints, as you might imagine from the assignment model, are the usual ones, which is no buyer receives more than one home, no seller sells to more than one buyer. Okay. I'm maximizing total value. What do we know about the assignment model? We know the constraint matrix is totally unimodular, so all the extreme points are integral. Therefore, my integer program can really be solved as a linear program. Strong duality applies. I can interpret the dual variables on these things as prices and surplus, respectively. Okay. I can solve the dual problem to work out the prices and the surplus. There is still a notion of a lowest market clearing price and a highest market clearing price, even though we're talking about vectors of prices, because the vector of optimal dual prices lives in a lattice. So there is a well-defined notion of minimal and maximum. There is a core. Every competitive equilibrium allocation is in the core. Everything in the core is a competitive equilibrium allocation. The point in the core that maximizes the surplus to the buyers gives every buyer their marginal product, so we get the incentives aligned as well. So everything goes through for this housing model because of total unimodularity of the underlying constraint matrix. Now let me go to the other extreme of Shapley-Shubik. This is called the Scarf-Shapley housing model. There is a set of agents. Each agent owns a house. And here is the preference information. Each agent has a strict preference ordering over the homes. I am no longer saying that there is a utility for the agent and that utility is denominated on a common monetary scale. Nor is this information I'm giving you telling you anything about the intensity of preferences. It's simply a rank ordering. I prefer house 3 to house 4 to house 5. There is no money. So not only do I not have quasi-linear preferences, I also do not have access to a medium of exchange. However, I do have property rights, meaning agents own homes. Okay. This is crucial. The agents own something that is of potential value to other agents. Okay. Now, what is the goal? The goal is to reassign the homes to the agents in some good way so that each agent receives at most one home and each home is assigned to at most one agent. An allocation of homes to agents will be denoted by the symbol mu, and I'm going to interpret mu of I as the home that agent I receives under allocation mu. So think of mu as simply a permutation because that's what an assignment of homes to agents is. And the permutation is simply a mapping from the name of an agent to the name of some other agent because I can identify the home with its owner. Why on earth would you be interested in such a problem? Well, this is the simplest example, non-trivial example that one can think of an economy with non-quasi-linear preferences and no medium of exchange. And so this is why mathematically it's useful to study. Okay. Does it have applications? Well, at a stretch, yes. So notice I said as a stretch. So here is the usual classroom example that is given for the housing model. An agent refers to a pair of individuals, one of whom needs a kidney, one of whom who wishes to donate their kidney. So think of the kidneys as houses. So I want a kidney and I have a friend who wishes to donate a kidney. So why doesn't my friend just give me their kidney? Well, perhaps their kidney is incompatible for me. There are other people out there in the community who want kidneys and who also happen to have friends who are willing to give up their kidneys. So an agent now is a recipient and donor pair. So I will simply refer to that as an agent. And agent is offering a kidney. So call kidneys houses. And let's suppose each of us has a strict preference ordering over the kidneys that other people are offering. Why might we have such a preference ordering? Well, I would prefer kidneys from healthier people than sicker people. I would prefer kidneys that are compatible with my blood type than those that are not. Okay. As I said, as I was telling you, at a stretch. Okay? Why is this a stretch? The reason this is a stretch is because, practically speaking, I do not have a strict preference ordering over other people's kidneys. What's perhaps more relevant is it compatible or not? Okay. And the other reasons that it's a stretch will become clear once I describe the analysis of the model in detail. Okay. Other possible application you could have in mind is students and student housing. So I received a housing spot this year. The academic year has ended. I am given the right to choose different housing. And so what is a house? A house is a slot in some student accommodation. And I have preference orderings over the other possible slots that are available. Okay. Again, why is this a stretch? Student housing is typically shared. And so my preferences may be a function not simply of the particular residence, but also who I have to share with. Okay. But, to begin with, good enough. Okay. Once again, we should ask, what is the planner's objective here? And I'm going to propose that the planner should be concerned with Pareto optimality. And so in the usual way, I will define Pareto optimal by defining what is not Pareto optimal. Okay. So an allocation mu, remember a permutation of the homes, is Pareto suboptimal if you can find another allocation such that for every agent I, what is this saying? Every agent I prefers the house they get under mu at least as much as the house they get under mu. And there is one agent who strictly prefers what she gets under mu than she gets under mu. Okay? That's the objective. Okay. Can it be written as an optimization problem? The answer is, well, one way you could do that is you could say, wait a second, Pareto optimal allocations can always be found by maximizing a suitable weighted sum of utilities. So you could say, oh, this is easy. It's an assignment problem. I just have to maximize a weighted sum of the utilities. Where do the utilities come from? Well, that's not a problem. I've got a strict preference ordering for every agent, so I can arbitrarily assign utilities. Now what's left is to choose the weights. This, of course, is the challenging problem, which is it is not obvious how to choose what is the right, maximizing any weighted sum of utilities doesn't necessarily produce a Pareto optimal outcome. You have to get the weights right. And searching for the weights could potentially be a difficult problem. Okay. Everyone with me so far? Okay. Now, I can propose a mechanism to find a Pareto optimal allocation, but that mechanism is going to rely on the preference information that the agents give me. So I have a second constraint. I need to be able to find the Pareto optimal allocation, but to do that, I need it to be in the agent's incentives to truthfully report their order. So second definition, a mechanism or an algorithm, I'm going to call it dominant strategy incentive compatible if it is a dominant strategy for everyone to report their true preference. So let me describe this using symbols. I want you to think of a mechanism as a function that maps the preferences that everyone reports to mu, to some permutation. So everyone tells me their preference ordering. I have n preference orderings. I plug that into m, and out pops a permutation. Okay. So I can think of a mechanism as simply a function that maps profiles of preferences to permutations. Okay. Okay. Well, now suppose this was the initial report, unprimed preference ordering. And according to my function, I produce the permutation mu. Now suppose Mr. I changes their reported preference ordering. This, because they've changed the input into my function, they may change the output. Okay. And now what I want to make sure is that if they change their preference ordering, what Mr. I gets cannot be any better than what I'm giving Mr. I under mu. In other words, I propose my mechanism, and then I recommend to each of you, tell me truthfully your preference ordering. Mr. I, suspecting that I am not entirely sincere, decides to misreport his preference ordering. What is the result? The result is that he will be worse off, or at least no better off. Okay. I want this condition to hold no matter what anyone else is reporting. Meaning, it doesn't matter whether the other people are lying through their teeth or not. No matter what anyone else is reporting, it is a dominant strategy for you to truthfully report your preference ordering. This is a strong condition. It's an appealing condition because if this condition holds, I do not need to build any model of what theories agents might have about each other. Because no matter what anyone does, you're better off reporting truthfully. So I'm asking for two things: dominant strategy incentive compatible. The other phrase that people use in this context is strategy proofness. So I'm asking for dominant strategy incentive compatibility and Pareto optimality. It is not obvious that there is a mechanism that would achieve these two desiderata. And remarkably, there is one. Okay. It is called the top trading cycle algorithm. And there is one other condition that I would like to impose, which is I want the mechanism to be individually rational, meaning no agent should end up with a house that is worse than the house they began with. Okay. This condition is needed to make, in some sense, the problem non-trivial, even if the other two conditions were around. This is the condition that respects the idea that agents own their homes. It is their property, and they can do with it what they wish. Okay. Any questions so far? top trading cycle outlook. Okay, a little bit of history. This housing model was proposed in a paper by Scarf and Shapley, but the actual algorithm that I'm going to describe is due to David Gale. You will find a description of the algorithm in the paper. Scarf and Shapley credit Gale for the algorithm. Their original argument for why a mechanism would exist with the required properties was much more convoluted. There is a formal description of the algorithm on the slide before you. Let me describe it informally while you read the slides. Every agent points to their favorite house. Now remember, a house is owned by someone else. And I said we could identify the house with its owner. So every agent points to their favorite agent. Well, this sets up a directed graph. In this directed graph, there must be a cycle, at least one. There must be a directed cycle. Otherwise, the graph is infinite, but there are only a finite number of agents. Now, what is special about this directed cycle? In this directed cycle, everyone is pointing to their most preferred house. So I point to Martin, Martin points to Lucas, Lucas points to Alex. So let me put that in a picture here. So I point to Martin, and there are two Martins, so let me be specific. I point to Martin Bickler. Martin Bickler points to Lucas, and then Lucas points to Alex, and then wonders of wonders, Alex points back to me. Now, the beauty of this cycle is that each of us wants someone else's house, but we don't all want the same house. So what does David Gale suggest? Go along the cycle and execute those trades. So I get Martin's house, Martin gets Lucas's house, Lucas gets Alex's house, and Alex gets my house. Each of us end up with our most preferred house. That operation is called clearing the cycle. Okay, so step one, everyone points to their favorite agent. There must exist a directed cycle. Pick any one, clear the cycle. Anyone who got a home walks away with that house. In the economy that is left, ask everyone, point again to your favorite agent among those who remain. Repeat. Eventually, this algorithm terminates by exhaustion in a finite number of steps. Okay. Everyone clear about the algorithm? Let's do an example to drive the point home. So I have 5 agents, and their names are 1, 2, 3, 4, 5. For each agent, I have given you a strict preference ordering for that agent over the other agents. Let's apply top trading. So Mr. 1 will point to Mr. 2. Mr. 2 will point to Mr. 3. Mr. 3 points back to Mr. 1. Mr. 4 points to Mr. 1. And Mr. 5 points to Mr. 4. Okay. Well, there is one cycle. Here it is. We clear that cycle. So Mr. 1, 2, and 3 each leave with their most preferred house. 4 and 5 remain, we then ask them, point again to your favorite agent among those who remain. Well, 5 will continue to point to 4, but 4 will now point to 3. Well, 4 cannot point to 3 because 3 is no longer available. 4 can point to 5 because 5 is available. We found the cycle, clear the cycle, no one's left, end of the story. Okay. Now, it's obvious that the algorithm must terminate in a finite number of steps. It is clearly simple to implement. Okay. 2 theorems. First, the top trading cycles algorithm produces a Pareto optimal allocation mu for every possible profile of preferences. Anybody care to take a stab at the proof? Okay, well, if you think about what the algorithm is doing, it's generating a sequence of cycles, at least in the version that I described. Only one cycle was cleared at any time. Okay. So let me write down the cycles in the order in which they were cleared. Cycle C1, cycle C2, cycle C3, cycle C4, and so on. If this allocation is not Pareto optimal, there must be an allocation in which no agent is worse off, and there is at least one agent who is strictly better off. Agree? Okay. Now, this agent who is strictly better off, where could they be? Well, let's call that agent I. Could agent I live in the first cycle that I clear? Well, in the very first cycle, everyone is getting their top choice. So agent I can't live there. Could agent I live here? Well, if agent I is living here, they're either getting their second choice or their first choice. Agree? Well, if they're getting their first choice, you can't make them strictly better off. If they're getting their second choice, well, the only way you can make them strictly better off is if they get their first choice. But then why didn't the algorithm give them their first choice? Because their first choice must live here. Someone else is getting it. If they get it, then that agent is made worse off. So Mr. I cannot live in the second cycle, and now it's clear. Mr. I cannot live in the third, fourth, fifth, or any of the cycles. So therefore, the output of the top trading cycles algorithm is indeed Pareto optimal. Assuming, of course, that the agents have truthfully reported their preferences. Because Pareto optimality is defined with respect to the preferences. Okay, how do we know that they're going to report their preferences truthfully? So this is the second theorem. If we think of this as a game where your strategy is to report a preference ordering, and the outcome of the game is the allocation produced by the top trading cycle algorithm, then is it a dominant strategy in this game for you to truthfully report your preferences? Intuitively, this seems right. Writing out a careful proof requires some thought. but the essential intuition works like the proof of Pareto optimality. So why, if it is not strategy proof, then somehow I can misreport my preferences and end up with a more preferred house. Okay, so let's suppose my preferred house is house number 1. So if I announce house number 1 and then I announce my second preferred house number 2, I don't end up with house number 1. So then I say, okay, what I'm worried about now is because I didn't end up with house number 2, maybe I don't end up with house number 1. Maybe I don't end up with my second favorite house because my second favorite house is taken by someone else. So what I could do is I could move my second favorite house to the top of my list, and maybe I get a chance at that house. Right? Does that make sense? This is the only kind of misreport that I would think about making, which is what I'm worried about is by being truthful, I don't get my most preferred house, but my second most preferred house I also lose because I wasn't pointing to it. Well, the answer is that cannot help you because you can only get a house if what's true. You point to the house, the owner of that house points back to you, or they point to someone who points back to you, or they point to someone who points to someone who points back to you. In other words, whether you get a house or not doesn't depend on whether you point to it. It also depends on what other people are pointing to. You changing your report cannot possibly change what the other people are pointing to. In other words, if there was a cycle that contained your second favorite house, changing who you point to doesn't change the existence of that cycle. Does that make sense? Now, I said this was a setup which involved no money, and there weren't even quasi-linear preferences. But there is nothing to prevent me from introducing artificial currency. So consider the following thought experiment. I'm going to give every agent a budget, and I'm going to assign every house a price. And basically, actually, let me do it more carefully. I'm going to assign to every house a price, and that the price of your home will then become your budget. And then I'm going to allow you to buy whatever is your most preferred house that meets your budget constraint. Is it clear what I'm proposing? Okay. So here's how I'm going to choose prices. Every house in the first cycle, I'm going to price every house in the first cycle, I'm going to price at $1. Every house in the second cycle, I'm going to price at ½ Every house in the third cycle, I'm going to price at ¼ and $1/8, and so on. So I've announced prices for every home. I now tell each agent, I've given you a budget. Your budget is equal to the value of your house. So if your house is in the first cycle, your house is worth $1. You can trade it in for $1 and then use that dollar to buy another house. Well, which house will, if that's the deal I offer the agents, what's the resulting set of houses that the agents are going to choose? Well, if you own a house that's worth $1, it must be because your preferred house is also worth $1. And remember, you're only interested in consuming a single house. So the fact that there are other cheaper houses is irrelevant because you're not buying two homes. So if your house is worth $1, I know that one of your most preferred homes is also worth $1. And that's the home you're going to choose. If your house is worth half $1, you can't afford the homes that are priced at $1, but you can afford the homes that are priced at half. And you'll choose one of those. Now, the reason for this digression is to point out that even though there was no money, there really was. The homes themselves had value. If I had wanted to, I could have explicitly assigned prices to the homes as I just did. I didn't have to. It was enough for the agents to barter their homes. Any questions? Yeah. Continuing. What about stability? What is the incentive for an agent to participate? What is the incentive what prevents a subset of agents saying, you know what, forget this centralized marketplace for exchanging our homes. Why don't we go off someplace else and just trade among ourselves? Maybe we can do better. So again, I want a notion of the core, but I do not have transferable utility. I can still define a notion of the core, and here it is on this slide. An assignment mu of homes to agents is blocked by a subset of the agents if the agents in S, by trading among themselves, can find an assignment sigma that is defined on S, not the entire economy, such that every agent in S is no worse off, and at least one agent is strictly better off. Okay. Now, you can argue about this definition in the following way. You could say, you know, why not replace this by strict preference? Every single one should be better off. And the literature contains debates about what's the right way to deal with that. I'm not interested in that particular issue. I just want to highlight that that is something worth thinking about. In other words, when a coalition breaks away, is it enough that everyone be strictly better off, or is it enough that at least one person is strictly better off? Okay. Notice if you insist that everyone be strictly better off, it makes it harder to block. Right? It's clearly more demanding. So if I'm interested in robustness, then I might prefer this weaker definition. At least one agent is strictly better off. The set of assignments that is not blocked is called the core. And a little later today, I will show you that there's a way to think about this so that this notion of the core is consistent with the earlier notion of the core for transferable utility games that I gave you. Last theorem about top trading. The top trading cycles algorithm returns an allocation that is in the core. What's the argument? Again, you can probably see it relatively easily. What if it is not in the core? Then there must be a blocking coalition. So there must be some group of agents who, by trading amongst themselves, are no worse off, and at least one of them is strictly better off. Well, I don't know what this coalition of agents is, but supposedly one of them exists. So let me look and see in which cycle these agents inhabit. Maybe one of them inhabits this cycle, the other one inhabits this cycle, and maybe the other one inhabits a cycle over here. Okay, now, when they break away, they can only trade among themselves. Well, look at this agent here. They're in the second cycle. So they received either their first or second choice. There's no one else in this breakaway coalition that lives in that cycle. That means if they break away, they're going to end up with a worse house. So the only way this coalition, this breakaway coalition is going to work is if there is at least one other agent in the coalition who lives in this cycle. But then these two agents better prefer each other's homes to the homes of anyone else in the breakaway coalition, because if not, you need another agent in the coalition to be in that cycle. And if you repeat this argument, what do you end up with? You end up that the coalition is basically everyone. That's at least one way to structure the argument. To summarize, I gave you an economy with no money, indivisible goods, without quasi-linear preferences, but we were still able to find an allocation that was efficient. Notion of efficiency was Pareto optimality. That was stable, allocation is in the core, and in which agents had an incentive to truthfully report their preferences. So this perfectly parallels what I described in the case of a single object auction with quasi-linear preferences and money. My point is, it wasn't money that was important, and it wasn't quasi-linearity that was important. What was important is that the agents had something valuable to trade. Okay, now how is this related to kidneys? I said kidneys was a stretch in terms of an application. The first wrinkle is that in kidneys, preferences are not strict. And if you think about the top trading cycle algorithm, when there is indifference, you're going to run into problems, because if you ask me to point to my favorite house, there's an ambiguity, and it could be critical how I break the tie as an individual. Second, the other issue with kidneys is this: I produce cycles. Some of these cycles could be extremely long. In the kidney context, this is problematic because a swap of the kidneys typically requires simultaneous transplants, and there may be no hospital facility that can feasibly accommodate 10 or 12 simultaneous transplants. So there is really a constraint on the length of the cycles. So the actual kidney problem would be, I'm looking for a bunch of these cycles. Each of these cycles should have length no more than 4 or 5, that in some sense achieves some measure of efficiency. So what is the Pareto optimal set of trades subject to each trade taking place over a cycle of length no more than 4 or 5? That would be the relevant problem. And even that is a stretch because it's ignoring the dynamic aspects of the fact that houses arrive and depart. Any questions? I am now going to describe a model that contains the Scarf-Shapley housing model as well as the Shapley-Shubik housing model as a special case. Preferences will not be quasi-linear, and agents will have budget constraints. The extreme form of budget constraint would be your budget is 0, meaning there's no money, but I'm going to allow budget constraints. And all of the nice results that we have, meaning efficiency in the core, strategy proofness will still carry through. And the machinery will make use of optimization and lemma due to scarf, which I will describe in a moment. Sorry. Okay. This is the Kanzi housing model after Martin Kanzi. There are a number of other variations of this basic model. This is the one that I like because it has the cleanest. Okay, to my taste, it's the cleanest. There is a set N of agents. Each agent owns a house, and a house can be a dummy house. Each agent I is also endowed with a monetary amount WI, and the utility of an agent for a monetary amount Y and a house HJ is denoted by UI of YHJ. So you give me a bundle of house and money, I give you my utility. And the assumptions that we're going to make on the utility are they are continuous and non-decreasing in money, holding, house, fixed. A special case of this would be every agent owns a house and every agent's budget WI is 0. This would be Scarf-Shapley housing model. If I allow the utility function to be quasi-linear, meaning my utility for a house and some amount of money is equal to my value for the house plus money, that would be Shapley-Shubert, quasi-linear preferences. Okay? And WI would be infinity for Shapley-Shubert. Okay, this setup allows for budget constraints, and it doesn't require that preferences be quasi-linear. And if you look at the UI, the only assumption is a smoothness condition on the utility, and that utility should have the feature that if I decrease the amount of money I give you, holding everything else fixed, your utility cannot go up. Notice I am imposing no concavity assumption on the utilities. The key assumption is that every agent wants only one house. Now I have to tell you about core for environments where we do not have transferable utility. So let me first remind you about cooperative games with transferable utility. We have a set of agents, and associated with every set of agents is a function. Value of the coalition. What was the core? The core was divide up the value that you're giving from the grand coalition of everyone in such a way that no subset of agents has an incentive to block the allocation. Now, is the core always non-empty? The answer is absolutely not. Here's an example where the core is empty. Let's see, did I pick the numbers correctly? Oh, I didn't, sorry. Let me fix this. If you add up the last three constraints, it says that the sum of the z's must be bigger than or equal to 3/2. And that's clearly inconsistent with the first equation. So in this case, the core is empty. Since the core is a desirable property, it would be nice to know when it exists. And as I mentioned earlier, there's a characterization due to Bondareva-Shapley, which is simply an application of the duality theorem of linear programming. Let me go through it. So let me rewrite the core condition again. I want to know if the core is non-empty. Well, what I could do is I could solve the following problem. If the optimal objective function value of this problem that I am boxing in red is strictly larger than V of n, then the core is empty. If the optimal objective function value of this program is less than or equal to V of n, then the core is non-empty. Let me pause here so that you can convince yourselves of that fact. Let me give this objective function value a name. Well, now let me just write down the dual to the linear program that you see boxed in red. I'm going to assign a dual variable of lambda s. Just give me a second. I forgot in the slides whether I'm using lambda or delta. I'm using y. Okay. So let me use y. So for every subset S, I introduce a variable y subscript S. And now what would the dual be? The dual will be the following. Remember, there are no non-negativity constraints on the Z variables. So since the primal variables are unrestricted, all of the constraints in the dual must be equality constraints. And I'll pause here so that you can convince yourselves that I've indeed written down the dual to the primal problem that is boxed in red. Now, I'm sorry. Thank you, Halil. Next. Now I can state what is called the Bondareva-Shapley theorem. And once I state it, you're going to say, wait, you can get a named theorem for that? Don't ask me why, but historically, this is what it is called. Okay. Bondareva-Shapley. Core is non-empty if and only if there exist y's satisfying this such that, now if, I'm writing it the wrong way. If for all y's satisfying this, now, as theorems go, it's not clear what exactly is the content here. And Shapley spilt quite a lot of ink trying to find an interpretation to this problem that I am boxing in, I'm circling in green. So first, he called these y variables balancing weights. If you want an interpretation of these y variables, think of them in the following way. I have n agents, and let's suppose the y-s's were 0, 1. They don't have to be, but suppose they were. Then what is this constraint here that I'm underlining say? If the y-s's are 0, 1, I'm basically taking the agents and I'm partitioning them up into coalitions. Right? The y-s's represent a partition of the agents into coalitions. The fact that the y-s's are fractional means I'm allowing for fractional participation of an agent. So think of each agent as having a unit of time, which they can allocate to any number of coalitions that contain them. But the catch is that in any coalition S, all of the agents who participate in that coalition must contribute the same amount of time, which is Y subscript S. Okay. And you can read some of Shapley's papers where he will jump through hoops trying to give you a better interpretation than what I just gave you for these YSs. Okay? And I'm not about to try. I think it's a fool's errand. But I need this condition when I talk about cooperative games that involve non-transferable utility. Okay? So I want to generalize this notion of, not me, but others, generalize this notion of cooperative games to a world where utility cannot be freely transferred. So think of the Scarf-Shapley housing model. There is no obvious medium of exchange that allows me to transfer utility from myself to you. But we can still talk about the core in a way that subsumes this. Okay. non-transferable utility cooperative game. The choice of the word, the prefix non-transferable, I think is unfortunate. The right way to think about this is imperfectly transferable utility. It's not that utility cannot be transferred. It is that we're allowing for the fact that utility is transferred imperfectly. And what do I mean by that? When $1 leaves my pocket, maybe less than $1 arrives in your pocket. Imperfectly transferable. What is such a game? Well, there is a set of agents n as before. There is a v, but the v is no longer a number that represents the total surplus that the agents can achieve. The v is a set. So for every set of agents, there is a v of s, which is a subset of R cardinality S. The way to think about this is, if two agents get together, they can potentially bargain among themselves. The set of utility profiles they could achieve by bargaining among themselves is this set V of S. In the case of transferable utility, this set V of S has a very special form. In other words, the bargaining set looks like this. And anything on the line or inside the triangle can be achieved by the agents bargaining among themselves. Non-transferable utility allows for more general bargaining sets than just hyperplanes. And the way to interpret this is, I'm agent 1, you're agent 2, we bargain among ourselves, we might end up with an outcome here. And the horizontal axis is my utility, the vertical axis is your utility. What are the assumptions on these sets V of S? Well, if the set S is non-empty, then V of S must be non-empty, and it must be closed. And V of the empty coalition is the empty set. For every agent I on their own, there is a V subscript I, such that for all X's in Rn, X is in V of I. Now, here I'm abusing notation. V of I must be a one-dimensional set. X is an n-dimensional object. What on earth does it mean for an n-dimensional object to live in a one-dimensional set? And the answer is, it doesn't mean anything, which is why it's an abuse of notation. The way you should interpret statements like this is that I take the vector X and I project it into the one-dimensional space. So when I say that X lives in V of I mean the projection of the n-dimensional vector X into the ith coordinate plane lives in V of I. This condition simply says there's some upper bound that I can achieve on my utility on my own. Third condition, which is the one that has bite, is that I need this bargaining set to be what's called lower comprehensive. So in other words, if X is in the set, then any point Y below X is also in the set. This is basically free disposal. You are welcome to throw things away if you wish. And finally, a technical condition is I need this set to be compact. because I'd like to make use of things like continuity and the existence of maxima and so on. It's an abstract notion, so I think an example would be a good idea. There's a notion of the core, I'll come back to it. Let me do an example. 3 agents. The grand coalition can achieve anything in the following set that I am underlining in blue. So that's a 3-dimensional object. If agents 1 and 2 get together, then they can achieve anything in this set. Any other coalition of agents just gets the negative orphan. So there's an example of a non-transferable utility game. Now let me describe what the core is in a non-transferable utility game. It's the set of all payoff vectors that are feasible for the grand coalition. So that is the analog of the following condition in the transferable utility case. That cannot be improved upon by any coalition, including the grand coalition. So what does it mean to be improved upon in this setting? Well, pick an outcome in the grand bargaining set, X, then a coalition S can improve upon X if they can find an outcome Y in their bargaining set with the following property. Everyone is strictly better off. Now, let me remind you of what blocking was in the case of transferable utility. Blocking in the case of transferable utility was this. The total utility that the agents in S receive is strictly less than the total value they could achieve on their own. Notice this statement does not say that the individual agents are better off, but since V of S is strictly bigger than the sum of the ZIs, there must be a way to give every agent ZI plus epsilon. And because preferences are linear in the Z, every agent is strictly better off. Now, what is the core of a non-transferable utility game? It is this. Take everything in the bargaining set involving the grand coalition, and then throw out the parts that live in the interior of these smaller bargaining sets. So in other words, if this is one of the bargaining sets, smaller ones involving, say, agents 1 and 2, we're throwing out everything in the interior, but we are keeping the boundary. Now notice, if I pick some vector x in here, what does that mean? I take the projection of x down to the 1, 2 plane. The projection of x must live either here or on the boundary. In other words, when I pick the vector x and agents 1 and 2 decide to get together and see if they can do better, their problem is I'm giving them something on their Pareto frontier already. Anything else on their Pareto frontier is going to make one of them worse off relative to what I'm offering them in the grand coalition. On the other hand, if in the grand coalition I was offering them something here, in the interior of their bargaining set, that didn't come out very well. They could clearly improve on it by picking something on their Pareto frontier. So that's the notion of core for non-transferable utility. It contains the earlier notion of core as a special case. Let me go back to my example. I claim that the following vector, 0.5, 0.5, and 0, is in the core. Well, it certainly lives in V of n, agree. And notice it lives on the boundary of V12. So it's not in the interior of V12. And this point is clearly not in the interior of these either. Is there any group of agents that could do better? Well, 1 and 2 could get together. What does their bargaining set look like? It looks like this, but I'm giving them this. If they get together and they stay on their Pareto frontier, they either pick something here or here, but in either of those cases, one player is going to be worse off than before. So that's not going to happen. And the other bargaining sets are all over here in the negative orthant, and I'm clearly doing better than that. And here is a result of SCARF. An NTU game is balanced. If any balanced collection, so that means I pick any non-negative solution to this system. Those are balancing weights. So you pick a feasible solution to this, then over here, I pick all the sets S such that Y sub S are strictly positive. I need the intersection of these guys to be a subset of V of n. In other words, I can find a point in V of n, n-dimensional object, whose projection into each one of these lower dimensional objects lives in V of s. If this is true, if your game is balanced, then it has a non-empty core. Notice, unlike Bondareva-Shapley, it is not if and only if. It is a sufficient condition for non-emptiness of the core. Okay. So now that we have the language of stability, I can now outline sort of the argument in Kanzi's housing model. Okay? So there are two things to pay attention to. One, you need this notion of a core for non-transferable utility to make use of the fact that you're no longer in the quasi-linear world. And here is the second key idea in the analysis of Kanzi's housing model, which is we don't have quasi-linearity, so we need something that looks like quasi-linearity. And it turns out, we've known in economics for a while, there is something like that. It's called the expenditure function or money metric utility. And it crops up in different places. And we're going to see how it works in a moment. Okay? I need some notation. For any subset S of the agents, I want to denote by F subscript S all of the feasible ways of allocating the homes among the agents. So F subscript S is basically the set of 0-1 solutions to this system. So it's all of the ways of allocating the homes in the sub-economy consisting of the agents in S. An allocation in the Kanzi model consists of two things. It consists of a specification of who gets what house, that's the X, and who gets how much money, that's the YIs, and the total amount of money that's given out cannot exceed the money that's available. Right? Because in this model, we're handing out both homes and money. So once again, important to distinguish. There is feasible assignment of homes. Allocation specifies who gets what home, but also who gets how much. And I need A of S to be the set of all feasible allocations involving the agents in S. And the core would be the set of allocations in A of N, such that no subset can find an allocation in A of S that makes them strictly, that gives each of them strictly more utility. Here is a formal definition of what those bargaining sets look like. So a set of utility vectors is achievable by a set S if you can find an allocation, both money and assignment of homes to agents, so that every agent ends up with a utility that is at least VI. Okay. The way to think about this is in terms of an algorithm. I hand you a vector of utilities, one for each agent in S, and I ask you, is there an allocation that gives to agent I a utility of at least VI? This set is closed, it is lower comprehensive, that comes from the continuity, the closedness comes from the continuity assumption on the utilities. The projection of this into V of S less the interior is non-empty and bounded, also individually rational. Here is the second key idea. Kanzi defines the following object. Pick a target level of utility that you want every agent to achieve. So there's one utility for each agent, so that's a vector. I'm going to call that vector of utilities little v. Okay. Notice the index I and J. So this is the least amount of money that I have to give Mr. I so that the utility he enjoys from owning home J is at least VI. Okay. So think of it this way. Mr. I says, I want a utility of VI. And I say to Mr. I, you have to take Mr. J's house. Then Mr. I says, okay, you have to compensate me for that. How much? The least amount of money necessary to bring Mr. I's utility up to VI. The inf exists because I've assumed utility is continuous. In fact, the minimum exists because I've assumed utility is continuous. Okay. Because I have not ruled out the possibility that the utility may have flat portions, there could be, right? There could be multiple monetary values that deliver the same utility, but I'm looking for the least monetary value. that delivers a certain level of utility. And now here is the simple piece of mathematics from linear programming that we're going to make use of. A vector V of utilities is achievable by a group of agents S if and only if you can find an assignment of homes to agents in S such that the following is true. Again, think of this in terms of an oracle. I come to you and I say, look at the agents in S. I want Mr. 1 to get V1. I want Mr. 2 to get V2. I want Mr. 3 to get V3. Is there a way to assign homes and monetary amounts so that that is possible? Well, obviously you want to assign the homes to the agents so as to minimize the total monetary compensation that you have to give them to hold a particular house. And if the total compensation exceeds the total amount of money sloshing around among the agents in S, then I can indeed give the agents in S the vector V of utilities. Any questions so far? So this is really the key. This is what I think is important. Okay. You're turning a problem which doesn't appear to be quasi-linear into something that has quasi-linear aspects. Notice this problem. This is really just an assignment problem. So we can make use of total unimodularity to know that there is an integer solution to this problem. And finally, where does the core come in? It's simply this. If you can prove the following lemma, which is really straightforward, let Y be balancing weights. Let me remind you of what balancing weights are. So Wij's are arbitrary numbers. So this is a purely technical lemma. It says that if I minimize over the grand coalition, a minimum weight assignment over the grand coalition, that has total objective function value less than the following. Solve the same minimization problem over every subset, weighted by the balancing weights, and add that up. This is basically a convexity condition because if you look at these YS's, for each I, these are non-negative numbers that add up to 1. So what I put down here is really no more than a simple consequence of convexity. That, the argument here is in the slides, okay? That tells you that you have a balanced transferable utility gain. Okay? And I'm out of time here, so I should stop before I strain your patience even further. And let me get to the climax. So this analysis says that the core is non-empty. The same machinery of the MIJs allows you to show that a competitive equilibrium exists. You can find it using a sequence of shortest path algorithms. So you get competitive equilibria, you get core. Incentives, though, are a little harder. That analysis is more difficult, but there are theorems that tell us that once again, there is a way to choose the competitive equilibrium prices that gives the agents an incentive to truthfully reveal their utility functions. So the point is, whatever results I had for the single object, quasi-linear, unlimited amounts of money, they hold even in this case where there were multiple objects, non-quasi-linear preferences, imperfectly transferable utility, and budget constraints. The only assumption really that was maintained all the way through was unit demand. No agent was interested in consuming more than one object. And that really is the only important, that's really what drives everything. So to summarize, indivisibilities are never a problem as long as nobody is interested in consuming more than one object. The difficulties arise when they consume more than one object, and therefore the research goal is how much of what I've described can we extend to the setting where agents have multi-unit demand. So let me end here and take questions if there are any. Yes, Alex.
This is a tiny remark, but if I remember correctly, to get competitive equilibrium in Quincy, you did need some extra assumptions on money, right? It's not enough to just say that it's utilities non-decreasing in money. You
need it to be strictly increasing in money. Yeah, you need an additional condition to get competitive equilibrium, and that's related to the fact that you get these flat points in the utility function. But I suspect you can probably go back to Martin Kanzi and then rewrite the statement as I wanted what McLennan, for example, calls free disposal equilibria, right? So it's a way of selecting the equilibria so that, right, because there's this general issue when utility functions have flat regions, then competitive equilibria are no longer guaranteed to be Pareto optimal. But what you can do is you can select from among the set of competitive equilibria in a way that does give you Pareto optimality. And so my guess is one could probably just port over McLennan or Mascalel or these other results to the Kanzi setting.
Can I ask an actual question? Where did compactness show up in what you were doing, or did you?
The compactness shows up in the compactness shows, I think the issue is being able to define the interior. Right, because I want things to, right, I want points on the core to be on the boundary of these bargaining sets. So I need them certainly to be closed. Right, and then the boundedness is because it's the usual reason you want to avoid things going off to infinity.
So it's even in the definition. Okay, perfect. Thank you.
Yeah.